My name is Carrington the Genius, and today we are going to be talking about data storage and management in microservices. This is part of an ongoing microservices research to create a standardized way to store and manage microservices data. So today we are going to be looking at different data storage scenarios in microservices, and we are going to be talking about 7 of them. Now, in case you are joining me for the first time and you've not subscribed to my channel, please hit the subscribe button below. Feel free to also leave me a comment, like and share this presentation so that we can get to as many researchers and developers as possible. Today we are going to be looking at 7 different microservices data storage patterns, and one of them is database per service. We also have shared database, the Saga pattern, the API composition, the CQRS, the domain event, and event sourcing. So let's start with the first one, which is database per service pattern. As the name implies, in this case, each microservices data is kept private to that microservice and only accessible via that microservices API. In this case, a service transaction only involves its database. There is no room for a service to move across to another database in another service. Here, the service database is effectively part of the implementation of that service, and it cannot be accessed directly by other service. Now, there are different ways to keep the microservices data private to that microservice. You actually may not need to have a full-fledged database server for each of the microservices. The options are private tables per service. In this case, each service owns a set of tables that must be accessed by that service. Then we also have the schema per service, which is supported by a number of database management systems, and in this case, each service has a database schema that is private to that service. And of course, we have a database server per service pattern where each service has its own database server. In this case, this will be the last result. The reason is because private tables per service and schema per service has the lowest overhead and of course the lowest cost and lowest throughput in data flow. So using schema per service is appealing since it makes the ownership very, very clear. Some high throughput services might need actually their own database, and this is the last result where you have a database for each of the microservices. Now, there must be a way to create a barrier that enforces modularity, that ensures that databases or microservices don't go across to access databases in other services. For example, you could assign a different database user ID to each service and use a database access control in the database server to control access such as grants. If this barrier is not in place, it's likely developers and architects might actually bypass the service API and access its data directly. Let's now take an example of database per service pattern. In this case, we are trying to imagine we are developing an online store application using microservices architecture. Most services need to keep data persistent in a database. For example, the order service stores information about the orders and the customer service stores information about customers. Now, these are different services. The order service has the order table, the customer service has the customer table. But at some point, we might need to get the order details, which includes the customer name. In this case, what is going to happen is when you have a situation where you need data from 2 different tables, in this case, you need to get this data from the services API. So let me just take a pen. So the data will come from the services API from here to here. So if you have an order that has to include the customer details, you'll need to get that data from, it should actually be from here, from the API of the service. So you can't actually go directly to access this database directly. So you have to get it from the API to be able to use it to aggregate the information you want. So in this case, we are talking about database per service pattern. Now, what are the benefits of the database per service pattern? Using database per service pattern has the following benefit. It helps to ensure that the services are loosely coupled, and which is a big benefit of microservices. Changes to one service's database does not impact any other services. Second, each service can use the type of database that is best suited for its needs. We have an example in case of a service that does a lot of text searches. That service could use a database Elasticsearch, which is a database search engine, and a service that manipulates a social graph could use a different database, in this case Neo4j. We also have some drawbacks of the database per service pattern. Some of them include implementing business transactions that span multiple services is not very clear and straightforward. Distributed transactions are best avoided because of the cap theorem. Now I'm going to explain the cap theorem in the next slide. Moreover, modern NoSQL databases don't support a shared database per service pattern. We have a second drawback, is that implementing queries that join data that is now in multiple databases is very challenging. And finally, complexity of managing multiple SQL and NoSQL databases. Now, as I mentioned, I'm going to tell you about the cap theorem. The cap theorem states that it is impossible for a distributed data store to simultaneously provide more than two out of the following three guarantees. One, consistency, where every read receives the most recent write or an error. Availability, every request receives a non-error response without the guarantee that it contains the most recent write. And partition tolerance, the system continues to operate despite an arbitrary number of messages being dropped by the network between nodes. Now, since this is not a presentation on this theorem, I just want to mention the cap theorem because it's mentioned in the preceding slide. So we also have to talk about how do we manage inter-service transaction. Now there are two ways to manage inter-service transaction: API composition and command query responsibility segregation. There are various patterns for implementing transactions, and we talk about the Saga pattern in the next slide. Now these two implementation patterns are also discussed later in this presentation, and now therefore I'm going to move on to the next slide. We now have shared database pattern allows different services to access data from the same database, and sometimes it requires providing the same permission level for the services. So assuming you are developing an online store application using microservices architecture pattern, most services need to persist data. As I mentioned, we have the order service and we also have the customer service. So the shared database pattern approach uses a single database that is shared by multiple services. Each service freely accesses data owned by other services using a local ACID transactions. ACID means atomicity, consistency, isolation, and durability. Now let's take a typical example of the shared database pattern. In this case, we have the order service and the customer service. All right, so let me try to illustrate it. So let me just take a pen. So again, we have this order service. It has an order table. We also have customer service. It has a customer table. Now these two tables are in the same database. In this case, we are talking about shared database pattern. Granted, the order table belongs to the order service and the customer table belongs to the customer service, but all of them are in the same shared database with the same permission. Now, if we have a transaction where we have to select order details, here we can have a transaction that selects total orders from orders. In this case, we are selecting from this orders table, okay, and then we are selecting credit limit from the customer table, and then we are inserting into order table as well. So in this case, we have a transaction that spans different tables in the same database. The database will guarantee in this case that the credit limit will not be exceeded even when simultaneous transactions attempt to create orders for the same customer. So in this case, there is complete two-way communication between the two tables and consistency is guaranteed. There are some benefits of the shared database pattern, and there are two of them. One is that a developer uses familiar and straightforward ACID transactions to enforce data consistency. And second is that a single database is simpler to operate and implement. We have about 3 different drawbacks of the shared database pattern. One of them is development time coupling. Remember, the key benefit of microservices is that the services and even the data, they are loosely coupled. So a drawback of shared database is that a developer working on, for example, the other service will need to coordinate schema changes with the developers of other services that access the same table. So this coupling creates additional coordination and actually might increase the development time. We also have the runtime coupling. In this case, because all the services access the same database, they can potentially interfere with one another. For example, if long-running customer service transaction holds a lock on the other table, then the other service is blocked as well. And finally, the last drawback is that a single database might not satisfy the data storage access requirement of all the services. So in case of a service that actually runs well on a NoSQL database, in this case, is forced to use a relational database system, and that may actually slow down performance. Right, let's now talk about a new pattern called the Saga pattern. Now, the Saga pattern is a way to coordinate transactions or queries that spans across multiple databases or multiple services. So let's take, for instance, you have the database per service pattern, right? And each service has its own database. Some business transactions span multiple services, and you need a way to ensure the coordination and maintain data consistency. Let's also give an example using the e-commerce website, e-commerce application we've talked about before. So we have this e-commerce have customers, and the customers have credit limit. The application must ensure that a new order will not exceed the customer's credit limit. And since the orders and customers are in different databases, the application cannot use a local ACID transaction. So what we are saying is that we have the customer table and we have the order table here. So when a customer is placing an order here, we need a way to relate with this table so that we are able to maintain consistency while having good performance. So how do we solve this problem? So in this case, we implement each business transaction that spans multiple services as a Saga. So now what is a Saga? A Saga is a sequence of local transactions. We are going to illustrate it in the next slide. Each local transaction updates the database and publishes a message or event to trigger the next local transaction in the Saga. However, if a local transaction fails because it violates a business rule, then the Saga executes a series of compensating transactions that might undo the changes that were made by the preceding transactions. So this is how the Saga pattern works. Let's now take an example. So this is a typical implementation of a Saga pattern. So we have a Saga used here instead of two-phase commit. So we have a distributed transaction layer is created on top. So when a query comes, this query is placed in this layer and it accesses a Saga instead of accessing the database directly. Now this Saga now maintains a local transaction for each of the databases, and then these local transactions are made consistent, and they also work in a coordinated way. So there are two ways to coordinate this transaction made up of local transactions. One of them is choreography, where each transaction publishes domain events that trigger a local transaction in other services. And the second one is orchestration. In this case, we have an object called orchestrator that tells the participants what local transaction to execute. Remember, if there is a problem, there is a series of compensating transactions that rolls back all the transactions in the Saga. Alright, so let's take the choreography-based Saga. In this case, let's see, an e-commerce application uses this approach to create an order using a choreography-based Saga that consists of the following steps. Step 1, the order service creates an order in a pending state and publishes and other created events. So this is where we have in step 1 and publishes and other created events. The customer service receives the event and attempts to reserve credit for that order. So it receives the event and attempts to reserve credit for that order. Okay. It publishes the credit reserved event. Okay. Or the credit exceeded event. So it actually goes this way. Credit limit exceeded, meaning that the transaction failed, or the credit was reserved. So if this is the case, the order service receives the event and changes the state of the order either to approved or rejected. So based on the information that comes here, we now change the state of the order to either pending or, sorry, we change the pending state to either approve or reject. In the case of reject, a sequence of compensating transactions is executed to undo or to reverse all the steps that have been taken. So in this case, we have a choreography-based Saga. We also have an orchestration-based Saga. So this is also similar but a bit different. In this case, an e-commerce application that uses this approach will create an order using orchestration-based Saga, and the steps will be: the order service creates an order in a pending state and creates a create order Saga. So this is what we are doing. This is orchestration. So we have the order service creates an order in a pending state. So this is where we are, okay? And an order is created in a pending state at this point. So we have the state value or the state variable at this point. Right, the create order Saga assigns a reserve credit command to the customer service. So in this case, we have a reserve credit goes to the customer service. The customer service attempts to reserve credit for the order and sends back a reply. So this is what happens in this step, and the create order Saga, which at this point received the reply and sends either an approve or reject order command to the order service. So either approve or reject. Okay. So the order service changes the state at this point. This other state is actually changed to either approved or rejected or cancelled. So try to take some time to get your head around this orchestration-based Saga and choreography-based Saga. Now there is an advantage of the Saga pattern. In this case, it enables the application to maintain data consistency across multiple services without using distributed transactions. There's drawbacks of the Saga pattern. One of them is that the programming model for the Saga pattern is a bit complex. So as you can see, when we talked about the choreography-based Saga and the orchestration-based Saga, for example, a developer must design compensating transactions that explicitly undo changes made earlier in a Saga. There's also another issue, which includes that in order to be reliable, a service must atomically update its database and publish a message event. It cannot use the traditional mechanism of a distributed transaction that spans the database and the message broker. Instead, it must use one of the 4 patterns discussed next. Alright, so we are now going into some kind of different kind of patterns this time that are used to kind of compensate or make the preceding patterns we've discussed more robust and more efficient. We have the API composition pattern. Now, in this case, let's assume we have applied the database specific pattern. As a result, it is no longer straightforward to implement queries that join the data from multiple tables or multiple services. Remember, one of the problems of database specific pattern is complexity created by queries trying to join data from multiple services or sources. The question now is, how do we implement queries in a microservice architecture in this way so that it can span across services or across data stores? The solution is to implement a query by defining an API composer, which which invoking the service that owns the data and performs an in-memory join of the result. So this is an interesting thing that happens here. So you have a layer on top of all the services. So when a query comes, so this is a join query that joins data from different places. So that query comes, it has to hit the query composer. And this query composer stays in the memory and retrieves the data from all the services, more like splits the query into different queries for each of the services, and then aggregates the data again here in the query composer and then returns the data. So in this case, it's called API composition. All right, let's learn more about this API composition by looking at the benefits. So the benefits include that it is a very simple way to handle queries in microservices. However, there is also a drawback of this API composition. One drawback is that some queries will result in inefficient in-memory joins of large data sets. Remember, the API composer stays in the memory and queries are joined or aggregated in memory. Let's now go to this interesting aspect, which is command query responsibility segregation. You can say 2 more times: command query responsibility segregation, command query segregation, command query responsibility segregation, CORS or CORS. Now, this is also a way to make existing patterns more effective. So let's say we have the database per service pattern, and as a result, it is no longer easy to implement queries that join data. What do? How do we implement a query that retrieves data from multiple services in a microservice architecture using the database per service pattern? So the command query responsibility segregation says that we need to define a view database. A view database is a read-only replica that is designed to support that query. Alright, so the application keeps the replica up to date by subscribing to domain events published by the service that owns the data. Now we are talking about a different layer on top of the database of the data store, and this is called the view database, which is a replica of the data in the database, but created specifically to support the query that has been created. So instead of the query hitting the database, the query is going to hit the view database. I think I have a diagram to illustrate this at this point. All right, so we have, in this case, we have a situation where we are illustrating the command order responsibility segregation. So we have 2 queries coming: the find order history and the find order. So instead of this query to go to all these databases here, all these services, it doesn't go here, but it comes to this place. So we have the view database at this point. So this database is created specifically to manage these queries coming here as functions in the application. So we maintain this database right here, and these services here provide this data from them to this data to this view database, and when a query comes into the order history service, it simply goes here and gets this particular data it is looking for. When this data changes in these databases, it is updated. In the view database store. So this is command order segregation, responsibility segregation, command query responsibility segregation. The command query responsibility segregation has the following benefit. It supports multiple denormalized views that are scalable and performant, improves separation of concerns, and simpler command and query methods are necessary in an event-sourced architecture. The drawback includes that this pattern has increased complexity and also potential code duplication, as you have seen, and replication or lack eventually consistent views. Let's now look at another pattern called the domain event. This is derived from the domain-driven event. Again, this is a pattern that can be used to make existing patterns more efficient. So let's say that a service often needs to publish events when it updates its data, as we have seen in the previous CQRS pattern, where services have to publish an update to the view database. These events might be needed, for example, to update the command query request responsibility segregation view, which I call the database view. Alternatively, the service might participate in a choreography-based Saga, which uses event for coordination. So just take it as easy as the services is just updating some in-memory or some view that provides data for an incoming query. So the question is, how does a service publish an event when it updates its data? How does it do that? The solution will be to organize the business logic of a service as a collection of domain-driven design aggregates that emit domain events when they are created or updated. The service publishes these domain events so that they can be consumed by other services. And now if you go back, you can see what we are talking about. So when changes are made in these services, they publish an event at this place, an event handler, and this event is used to update at this point. So now we are talking about domain events. So so these domain events is simply a way, talking about a way to update a temporary or a view database from existing services, and this view database is actually where the query is going to actually be coming. We then have something called event sourcing. This is also an interesting one. It's also a way to make existing patterns more efficient. A service command typically needs to update the database and send message or events. For example, a service that participates in a Saga needs to atomically update the database and send messages. And similarly, a service that publishes a domain event must atomically update and aggregate and publish an event. The database update and sending of the message must be atomic in order to avoid data inconsistency. And however, it is not viable to use a distributed transaction that spans the database and the message broker to atomically update the database and publish messages or events. So the question is how to reliably atomically update the database and publish message or events. So this is also similar to domain events, but in this case we are talking about publishing both messages and events in such a way that there is atomicity and also there is consistency. The solution is going to be to use event sourcing. So how does it work? It persists the state of a business entity such as order or customer as a sequence of state-changing events. So whenever a state of a business entity changes, let's say a new order is created, a new row is created on the table, then it means that a new event is appended to a list of events. Since saving an event is a single operation, it is inherently atomic. So when a new request comes, this request is broken down into series of atomic events which are executed one after the other, and the application reconstructs an entity's current state by replaying the event. So each time application persists an event in an event store, it means that a database actually have been updated or a change have occurred. So we have an example of event sourcing. In this case, we are also using customers and others as an example of the application that is built using event sourcing and CQRS. The application is written in Java and uses Spring Boot. Okay, so let's look at this in this case. So in this case, we have let me take my pointer. So we have another service, and we have this other service, and when a query is created that spans multiple databases, this is what we have. So we have an event store. We simply maintain an event store, and we maintain this event as a sequence of events, and it represents an order. So when this sequence of events is executed one by one, we are sure that database consistency is maintained. So we also have some benefits of event sourcing, and one of them is that it solves the problem of implementing an event-driven architecture that makes it possible to reliably publish events whenever a state changes, and because it persists event rather than domain object, it mostly avoids the object relational impedance mismatch problem. It provides a 100% reliable audit log for the changes made to a business entity. It makes it possible to implement temporal queries that determine the state of an entity at any point in time. Event sourcing-based business logic consists of loosely coupled business entities that exchange events. So let's look at the drawback as well of event sourcing. I think there should be just one problem with event sourcing. Let's see. So event sourcing has several drawbacks, about 2 of them. It is different and unfamiliar type of programming, and so there is a learning curve. The event store is difficult to query since it requires typical queries to reconstruct the state of the business entities. So that can be complex and inefficient. So let's recap what we've learned so far. We've learned about 7 different database storage patterns for microservices. So I can just try them out so that we keep them in mind. So the first one, take a pointer. The first one is called the database per service. The second one is shared. And we also talked about the Saga. Then we talked about the API composition, and we talked about the CQRS, which is a so CQRS represents command query responsibilities segregation. The CQRS, yeah, that is fine. And we also talked about the domain events, which is derived from domain-driven design, and then we talked about the event sourcing. I'm going to stop here. I'd like to recommend that you take some time to get your head around it. You can get more details about this database storage patterns for microservices. You can get it from literature. If you have some challenges, you can also let me know by leaving me a comment below. As I mentioned, if you've not subscribed, hit the subscribe button so you subscribe and get updates when I make new presentations like this. I'd like to thank you for viewing, and I remain Kindson the Genius.